Okay, ladies and gentlemen, this is still section 8-1. This is recording number 5, and I discovered I made a mistake. I falsely said on recording number 4, I said that it was number 3. And I don't know how to edit very well at all, so I'm going to have to leave that alone for the time being, and hopefully I can make that change a little bit later on. So this is definitely number 5 that I'm on right now. The one that I have 2 of them that I said was 3, but the reality is one of them's 3 and one of them's 4. Sorry about that. Okay, so here we are, example 8-2. Examples are great. If you're not doing these examples with a pen and paper in your hand and writing out all the details, you're making a big mistake. I know I've mentioned this many times, but please trust me on this. This is how you learn the material. You've got to do this. So get your pencil and paper in hand, read through this after I talk about it, and make sure that you understand how to do every single step. In the long run, I promise you, you will save time. So here's an example 8-2. We're going to use table E. That's the table that is for the Z scores, the Z distribution. And we're going to find the critical values for each situation, and we're going to draw the appropriate figure. Okay? So left tail test, alpha is equal to 10. So first thing we do is we draw our cartoon. Alpha is 10. That means that over here is 10% chance of being wrong. Now you notice the problem A said a left tail test with alpha is equal to 10. So that's how come we know it's over here. It's a left tail. That's where the possibilities for errors are, is over here. The concept is that, like if we were talking about, something where the alternative hypothesis was that it was less than a certain mu, well, that's where we can make our errors. If our sample data came out and the sample data said, oh gosh, the sample data, the x bar is greater than the hypothesized mu, well, we would just reject it. We'd say, well, the heck with this. Obviously, we can't possibly be right. Our research, our hypothesis is clearly wrong because this x bar came back exactly the opposite of what we expected. We need to go back to our drawing board. We need to think this thing through a little bit better. Okay, that's kind of the concept. That's why we can have a one-tail test. Otherwise, why wouldn't you always have two-tail tests, right? Okay. All right. So we draw the figure. Here's our cartoon. We draw in our shaded area here. That's the 10% that we can be wrong. And what we've got to do is we've got to find the Z value such that to the left of that Z value, there's 10% of these values. This distribution, the area under the curve is 10%. So you go and you look at the table and you find what Z value gives you that corresponds to the area of 10%. Now, it's not going to be exact, as he points out here. It's actually 0.1003. So that's not exactly 10%, but it's as close as we're going to get. And what's the value? It's negative 1.28. So that is our cartoon. That's our critical value. So what we're going to say here, just looking ahead, we do our statistical test and we end up over here, we're going to reject the null hypothesis. If we ended up over here, any place to the right of this, we would not reject the null hypothesis. Okay, so now B is a two-tail test. Alpha is 0.02. So it's a two-tail test. That means you can be wrong over here, you can be wrong over here. What you're saying is, like in the blood pressure medication, you're saying, hey, I think that the blood pressure is going to change with this medication. I don't know if it's going to be more, I don't know if it's going to be less, or maybe it was pulse rate, I guess. It was a pulse rate. So the pulse rate is going to change. It's going to be more, it's going to be less. So if I'm over here, I reject the null hypothesis. If I'm over here, I reject the null hypothesis. But wait, the human beings are involved. It could be just by random chance that I'm over here. I could be wrong some percentage of the time if I'm over there. I could be wrong if I'm over here by some percentage of the time. Maybe it just so happened that I ended up there. I made a mistake when I rejected the null hypothesis. It could happen. How often will it happen? I want it to be overall, I want my error rate to be 2%, or I'm sorry, I think it was 1%, right? Yeah. Hold on one second. Alpha is 0.02. Alpha is 2%. So I want it to be wrong 1% of the time if I'm over here, 1% of the time if I'm over here. So that's where I find those critical values. So this notation here drives people crazy, but it shouldn't. The alpha over 2 just means half of my budget. If I'm allowed to be wrong 2% of the time, I'm allowed to be wrong 1% over here and 1% over here. If I had said alpha is 10%, then half of it would be 5%, that would be over here, and the other 5% would be over here. It's a budget. It's how much you're allowed to be wrong, okay? And then what they say, this makes you crazy because he's not using intuition. He's just giving you a formula or a step-by-step process. That's okay if you have perfect memory, but for all the rest of us, we don't have perfect memory, it's better to have the intuition and understand it, okay? So for the left Z critical value, find the area closest to alpha over 2. So over here, the Z table, this critical value right here, to the left of this value is going to be 1%. That's what we know and love about the Z table. How about this Z table over here? Well, you really don't need to find it because once you find this one, it's symmetric. So if this one's negative 3.33, this one's going to be positive 2.33, okay? So you don't really need to find it, but he wants you to find it, so let's find it. The right Z critical value, it's going to be the area closest to 1 subtract half of my budget. Now, why is that? Well, think about it. If my budget is 2%, that means that 1% is going to be over here, 1% is going to be over here. So what critical value do I want for this? I want it to be 99% because 1% is over here, so 99% has to be to the left of 2.33 or whatever the number is. I don't know what the number is yet. I'm going to look it up. So whatever this critical value is, 99% is to the left. So I take 100%, take away the 1%, gives me 99%. So that's where this comes from here, is 1 subtract 0.02 divided by 2. The notation leaves a little to be desired here. Okay, but the intuition is just so easy if you just understand what these curves really represent, okay? All right, so that gives you this critical value and this critical value. The other critical value, we want it to be a one-tailed test, and we want it to be an alpha of 0.005. So, 0.005, half of that, or I'm sorry, we do not take half of that. The alpha is 0.005. So all of the error is over here. So 0.005, in other words, 0.5% is over here. So that means that 0.995 is to the left. That's the 1 subtract 0.005 is to the left. That's 99.5%. Okay, so you look in the table, and the best you can do is you can get these two numbers, 99.49%, 99.51%. So those two Z values that correspond to this and this are 2.57 and 2.58. Well, it's halfway between, so you can find the average of those if you want. But what most people do is they'll just say, the heck with it, let's just take the 2.58. That's further out to the right. That makes it even harder to reject the null hypothesis. So I might as well take the bigger guy, the guy that's out here, okay? All right. So these are the steps. He gives you the steps in a step-by-step process here. And for crying out loud, make sure you do this. State the hypothesis. So many times people are just wandering around and working in circles. They can't even state what the hypothesis is. If nothing else, you must be able to state what is the hypothesis, the null hypothesis and the alternative hypothesis. So many times you see on TV people, they can't even say what the hypothesis is. What are you trying to test? They don't know. It's absolutely ridiculous. Okay, then the next step is designing the study. You've got to select the correct statistical test. Now, we haven't even talked about that yet. That's coming up next. We haven't decided, or we haven't talked about how to use the correct test. But that's what you have to do. You have to select the right one. This is important, selecting the level of significance. How right do you want to be? What kind of errors are you willing to tolerate? Are you talking about how many push-ups the kids can do, or are you talking about somebody's going to die if you're wrong? That makes a big difference, what the level of significance is. And then you got to formulate a plan to carry out the study. I mean, how are you going to test these kids doing push-ups, right? I mean, how are you going to make sure they eat their Wheaties? Those are all the important things. Those are important things that if you don't get right, the study is not valid. I mean, how do you know those kids are eating Wheaties? You know, how do you know? Maybe they did, maybe they didn't. That'd be an example. On medication, how do you know people took the medication? How do you know that? Okay. Do they do something else? Do they have what's called lurking variables, that they did something else that could cause the results to be different? So this part here, formulating a plan to carry out the study, there's whole books written about that. There's guys that get their PhD doing that, okay? So we're not going to learn how to do that in this class, but you need to be aware that that's an important step, okay? All right, so this plan should include all of this information, okay? So then you conduct the study, you collect the data, you evaluate this data. So I think this is pretty darn clear. He wrote it very clearly. Okay. All right. So this is truth in advertising. It's a simplified version, okay? We're not going to design the study. We're not going to collect the data. We're not going to do those things. We're going to just go ahead and learn how to do these hypothesis testing. Okay, so here's the blue table here. There's a procedure table. You state the hypothesis, find those values, compute the test value. These two terms sound alike and they get mixed up all the time. Critical value, that's the test. The critical value is this guy right here. That's what you say, okay, that's my critical value. If I'm past that, I'm going to reject the null hypothesis. That's my critical value. The test value is different. The test value comes from your data. You gather the data, and from that data, you do the appropriate test, the appropriate formula, I should say. Let me start over. You gather your data, you look at your data, you calculate certain things, standard deviation, the mu, whatever it is you need to do, and then you use that information in the formula, and then that gives you a number. The output of that formula is a number. That's called the test value. And then you decide whether to reject or not reject the null hypothesis based on comparing the test value to the critical value. If you're past the critical value, if your test value is past the critical value, go back up here, if you end up over here with your test value based on the data, you reject the null hypothesis. So that's why if you do it right, you know, it's very algorithmic. You know, it's like watching the Kardashians while you're doing it. There's no problem. You've already made your decision about how to conduct the study. Okay, so here's the little summary here. Okay, gosh, he just keeps on going here. Okay, so he talks about what's the difference, you know, again, another example. But here's very important statement. Nothing is being proved true or false. You're only stating that there is or is not enough evidence to say that a claim is probably true or false. It's not proof, okay? And typically, what you're really doing is you're just saying, hey, there's enough evidence to reject the null hypothesis. So, if you reject the null hypothesis, that doesn't mean that the alternative hypothesis is true. It just means that there's enough evidence to reject the null hypothesis. Now, we're going to get into this in a little bit, and you'll see how there's a lot of wisdom in those words that I just gave you, that I just quoted from him. You know, it is a big distinction between merely rejecting a null hypothesis versus saying, oh, the claim must be true. That's not the way it works, okay? All right, so that's the end of this recording. So that's the end of section 8.1. So I'll get this posted here, then we'll get started on 8.2 here shortly.